Hi, my name is Pim Sarlos. I work as a product owner for Keda Group, and thank you for watching our presentation about the configure to order and design automation process. So let's dive in and talk about some industry challenges as we see today at our customers. With all the developments worldwide, politically, economically, and new technology, which is brought into the markets like AI, it's not easy to stay ahead on your competition and stay as efficient as a company. So in current times, we see a number of challenges that many companies struggle with. Finding the right balance between product leadership, customer intimacy, operation excellence, it's not easy. So let's talk about some more specific challenges for the manufacturing industry. So application customization causing unneeded downtime, leading and errors troubleshooting. One-person armies and external dependencies, loss of data, double and manual workload, no reuse of data, long lead times in sales and engineering processes. Or common challenges in the construction industry. Global earnings before the interest and tax on construction activities is just like 5.5%. So even the smallest mistakes can make or break the project. And projects are becoming increasingly more complex, yet the schedules keep shrinking. So 80% of the construction companies cannot find the workers they need. Teams are becoming more and more distributed with stakeholders split between various offices of the field. And we believe that adopting a configure to order strategy in your company will help you to overcome these industry challenges. So let's take a deeper dive in what we mean with configure to order. And when we look at our customer processes, we recognize in general three types of primary business processes. We identify these processes as configure to order, engineering to order, and design to order. There are two main differences that separates these three types of processes in how they can be recognized. The first difference is about the moment in time when the required product data is being created. So for CTO, the product data is already prepared and available upfront in the process. For ETO, some adjustments or small new designs are created after the order is received. And for DTO, design to order, more development cycles are required. So the actual useful data is being created at a later stage in the process. And the second difference is about the amount of people that are involved in these processes. So for the CTO process, very little people can be involved since the product data creation can be automated. It goes directly from sales to the production department. ETO, engineering to order, has mostly sales engineering and engineering involved to get clarification on requirements and specifications. And within DTO processes, the new functionality can be designed, which involves the R&D department, and additional support is required from all other departments to come to a new functional product. At this slide, we see two main processes often defined as ETO and DTO. And both processes begin with a customer and a salesperson getting clarity and an agreement on the commercial and technical requirements. Once there is an order, the engineer starts by designing the product. And once new functionality is required, R&D people join the process. When the product is released, work preparation and purchasing can start with calculation and purchasing components. And if all the required components are produced and being delivered, the assembly process can start. After testing, the product can be commissioned and installed at a customer site, and maintenance is being transferred to the service organization. Within these processes, people speak about a product referring as one-of-a-kind product, specials, or customer-specific solutions. And in the bottom, we see how these processes are being experienced by the people within the process. And due to all kinds of missing information and unclarities within the specification process, a lot of communication and rework needs to be done to be able to deliver a functional product. It appears that every time these processes are being executed, they are being experienced for the very first time. So we have a better understanding. Let's take a look at some first-time experiences. So in the Netherlands, everybody is used to ride a bike. And then we have about 80 million people and 22 million bicycles. So to be able to survive on a bike in the Dutch traffic, we need to learn to ride a bike on a very early age. And how was it like riding a bike for the very first time? For me, it didn't work out that well. Yeah, how was yeah, as well as driving a car for the very first time. Yeah, the first time didn't go well either. So try to imagine what happens if we perform a cycling activity for the 1000th time. We have developed and prepared our equipment, we know where to go, and we know when to finish. We're able to improve by every time we perform the activity. It goes a lot better. And of course, the same experience for our Dutch national hero, Max Verstappen, when driving his Formula One car. He is able to improve by every training activity, almost every time now, but just keeping the repetition going, we're able to create product and processes, and we are able to automate them. So Mark is going to show you how configure to order can help you out, and it means a lot for the processes and people in your organization. So Mark, please introduce yourself.
Thanks, Pim. Thanks for the introduction of our CTO process. My name is Mark Brouwers. I'm a developer working at the same company as Pim, so we are colleagues at Kadek. So I want to continue with the technical in-depth information on how we achieve this CTO process. So let's show some of the language that you will have to learn when stepping into the CTO world. A lot of new words will be introduced in the organization. And afterwards, everybody looks a bit like this, because there are a lot of difficult words when you first see or hear them for the first time. So we got like a product mix, modules, variants, configurations, product platform. Let's clarify some at the use of some examples. The most modular product ever, Lego. Imagine the Lego car on the right side of the slide as one of the specific products of your customer. For a manufacturing company, this product could be a machine. For a construction company, the product can be a house. Every product consists of some typical components. These collections of components we call modules. In general, we see that a module is a generic collection. It has no physical representation or identification. So on the screen, we see 5 modules. A front module, an engine module, a chassis module in the center, a body module, and an access module on the right side. When we zoom in on the front module, we can imagine this module comes in different representations. Within the highlighted circle, we have a front car executed with a radiator. We call this a variant of the front module. Next to the radiator variant, we also have a variant without a radiator. This is a second variant highlighted in the circle. So horizontally, we speak about modules. These are generic. And vertically, we speak about variants, and these are specific. In the case of variants, specifications are known. The costing involved are known. We know the interaction between other variants, and we are able to define their interfacing. As you can see, there's one exception. The chassis located in the center of the slide. There is only one variant of this module. So this means that every car uses the same execution of the chassis. So this makes some people very happy. All right, to create a product, we need a certain set of interfacing variants which can be combined. The product in the yellow circle on the right, we call a configuration. So if we want to create a different product, we use a different set of variants to create a different configuration. So the collection of all those variants, we call this a product platform. It is important that the content of the product platform matches the market needs to a certain period of time. This is where the product management begins. In this example, the Lego product platform consists out of 11 variants. So this is the sum of all the variants. Instead of the sum, we can now multiply the variants. That gives us 36 unique product configurations. So with 11 variations, we can create 36 configurations. And we maintain the specifications and documentation of only these 11 variants instead of 36 end products. So that's a huge difference in terms of workload for the organization. This picture shows how to identify the type of product deviation in the product structures of a configuration. The CTO product configuration contains only variants from the platform. So it is a 100% CTO configuration. If the product contains any ETO or DTO specifications, the interaction with the other variants need to be validated at the product level. Of course, we embrace and stimulate the use of CTO variants within ETO and DTO products as much as possible. So the first thing a company should do when implementing a configure-to-order strategy is defining a product platform. In this example, we derivative of the product platform of one of our customers within the manufacturing industry. So if this is possible with Lego or within the manufacturing industry, why not within the construction industry? So imagine this example with facades, doors, windows, window openings, window frames, and bricks. In this example, we already have 324 different configurations as an end product for the facade. Let's take this at a higher level and look at the house. Take the roof, the facade, which is built up from the facade platform from the last slide, and take the house dimensions also in the equation. Now we can make millions of house configurations for our customer. I hope this will give you some inspiration about the possibilities for the construction industry. The basis of configure-to-order is always a good defined modular product platform. First, an overview of the traditional steps in the manufacturing process within an organization. Sales defines a product or project where an agreement is reached with the customer. Information transfers from engineering to work preparation and production. Once the product has been produced, it is transferred to the customer, and the service organization will take over responsibility and maintain the product. It sounds very simple, but the challenges and frustrations mentioned at the beginning of this presentation are present every day in these processes. All kinds of applications supporting a specific part of the process. We see that integration are most typically solved via point-to-point connection, a direct connection between two information systems. Point-to-point connections appear in many forms. For example, as commercial plugin, as manual export, as custom solution made by an external expert, or via some tool found on the internet. This tangle one-on-one integrations is not scalable into the future and very difficult to maintain. Managing point-to-point connections can be a challenge because they rarely come alone. In practice, many point-to-point connections exist in the form of scripts running on different servers, log files created on locations all over the place, etc. This is an issue since central overview is lacking. As a result, changed data still gets overlooked and related processes simply go wrong. The alternative is an integration platform with the objective of centralizing the data exchange between information systems by means of clear orchestration and the shared technology for setting up each point-to-point integration. Each organization is unique, as are related integration requirements. So in order to fit within existing processes, the system integration should be flexible. The flexibility can be offered by using a low-code platform. This slide is showing an overview of applications within an organization connected through an integration platform. Each application has a connector, a connection to the platform. There are many standardized connectors for the most used applications, but as long as the system has a REST API, a connector can be created easily. Within one or more scripts, the business logic to read or write information in the system is customized. Instead of a spaghetti of connections between applications, it offers a very structured methodology which can be expanded over time. For this presentation, we will focus on the CPQ, design automation in APS and PDM. The design automation process in combination with the PDM system is a very complex process, involving a very large number of automated actions. As a result, there are also many possible points of failure. If one part of the process fails, it could leave a mess behind with unused documents in your PDM system, and it will cost a lot of time to do this all over again. Therefore, we implemented a phased methodology in our design automation approach. The complex process is split up into 4 phases: prepare, process, assemble, and manage. We will take a look at each phase in a moment, but one thing to point out is that the flexibility of this phased approach. By splitting up the design automation process, we have the ability to outsource the processing part, where inventor or inventor server does the magic. The process phase in this case is offloaded to Autodesk Platform Services. Let's take a detailed look at the phased approach and how the whole process comes together. At first, the integration platform receives a message from an external system, in this case the CPQ system. Scala Connect acts as a conductor of the whole process through a so-called orchestration script. This type of script is capable of creating a task, and it will wait until the task reports back to the script. The first task that involves adding a preparation job to the Vault job queue. When the job is picked up by a job processor, it will take up the input passed on from the CPQ system through the integration platform. Input could be, for example, the product type to instruct Vault to create a copy design of a base model, the destination folder involved, and so on. It can also retrieve templates and design data to ensure that the next phase has all the input necessary to be processing. The gathered data is temporarily stored in a zip file in Vault. Then the job reports its status back to the integration platform, and the orchestration will start the next task. The second task involves the starting of a workflow in APS. So this workflow contains several steps. The upload of the activity definition. This has to be done because it has to be changed between two configurations. Uploading the app bundle. Same goes here. The app bundle could have been changed over time. Uploading the results of the prepare job to a bucket. The zip file containing the copy designed files is being placed to be able to that APS can reach out for them. Configuring a work item with the parameters from CPQ. Then start the work item. During this step, the custom code, so C# and iLogic code, will be executed and the copy design structure is formed into an order-specific model. Download the results from that work item into a bucket. Assemble all the generated models that are present in CPQ, so in your code. This type of task is optional and will only be required if two or more process products need to be assembled together. Download the final assembly with all the configurations and upload it into Vault, and notify the main orchestration in the integration platform that this phase has been completed. The fourth task involving adding a managed job to the job queue. The responsibility of this job is to check in the newly created inventor model. So when this job is picked up by the job processor, it will download the zipped processed assembled data from Vault, extract it to the workspace, and open it in Inventor. This type of task requires a full version of Inventor on the job processor machine because Inventor is required to correctly check in the CAD models and the 2D drawings into Vault. Once the check-in is completed, there is an option to automatically change the state of the models and drawings. In case of a CTO product, this is often the case. So in the case of an ETO product, the models and drawings remain in the state work in progress to allow an engineer to make manual changes. The nice thing to point out about the platform is that it can handle many tasks in parallel. In this example, you can see a separate timer script that runs every couple of minutes to monitor the job queue. And when there are more, let's say, 50 design automation jobs in the job queue, the script can start on an additional Azure virtual machine to help handling the jobs. With all this in mind, the system is capable of scaling itself up and down. How to configure the CPQ? Start a video to show what the CPQ a product can be generated. You select a product in CPQ that you want to configure. In CPQ, you enter some customer information. So this could be integrated with a CRM system. Then you select your product. You start from a predefined configuration. Once as a starting point. Afterwards, you can use this default configuration and start adapting something. In this case, when you change the length of the antenna, the system knows that it's no longer CTO, but it switches over to ETO. You define why the reason you have to change it to an ETO. Additional, you can per product specify which type of engine, this Autodesk engine you want to use, Inventor server of APS, and even the version. You can even change some custom parameters. Once finished, you save your final product definition to the quote. You enter a quote identification, and you start your workflow. So by submitting this quote, you will start the workflow in CPQ. It comes to a state ETO because it was an ETO product. So the main engineer approves this quote and will start in the state building the model. So what we can do in CPQ is define the engine to be used so that the flavors and even the version that you want to use, and you can alter all parameters of your product configuration. So we now have in CPQ, we have a quotation with, for example, 6 cars present, so that have 6 configurations that have to be created during the process. How is the CPQ data transferred into the workflow in Connect? So depending on the structure in CPQ, the JSON fragment is being constructed in the workflow of CPQ. For each configured product present in the quote, a configuration has to be created by inventor. At the same time, some parameters necessary for the organized fault design automation jobs are pushed towards the orchestration. Parameters like numbering scheme, assembly name to copy design from, the app bundle to use, etc. Once the orchestration is started, its implemented workflow will create the different types of fault jobs in Vault. These fault jobs will execute its implementation and use the callback URL to signal when the job has run. This external information is processed inside the orchestration. The ladder will cherry-pick this information for each stage in the process. Since nowadays, most of the job processors resides in the cloud, and they can be started, stopped when needed. As soon as the main orchestration is triggered, a first check is performed to see if any job processor is running. If not, then start the machine, and if there are too many jobs waiting, start an additional one. So the main orchestration receives a list of available machines to pick from. Within CPQ, there's a workflow active. So as soon as you submit your code, this workflow is started. At a certain moment in this workflow, the quote triggers a function in Kala Connect. The main orchestration is launched and foreseen with the necessary parameters as indicated in the previous slide. So the first task of the orchestration is uploading the activity and upload the app bundle to APS. This app bundle was stored in Vault. So this is mainly a user interface-less process. I will show you some of the logging. So here is the URL triggered, the main orchestration is triggered. And as you can see, there is an app bundle uploaded, and the activity is uploaded into APS and set ready to be used by in a later phase in the process. So as soon as it reaches the stage of creating the Vault jobs, so the prepare job makes a local copy design of an assembly that you specified in your CPQ system. It makes a local copy design, but with Vault numbers generated from Vault. The copy design structure is afterwards packed and go and stored in Vault as a zip file. The zip file will be used in the second step when the CAD model is being processed. So the logging indicates that you got 2 process jobs. So on the job processor, this job is being picked up and being executed and starts doing its work by making a copy design of a predefined assembly. And as soon as prepare job finishes its work, the main orchestration in Connect is notified and indicating that the job has done its work, and the next phase in the process can start. The next phase consists out of uploading the packed and go prepared data into a bucket. We create a work item and assign its parameters with data from CPQ. We're going to start the work item and download the results as a zip file as soon as the work item has finished, and we place that result back into Vault. So a work item is created and started in APS. Data is uploaded to the bucket. The work item is started. We go check to see what it's doing. We get a report when finished. Let's see what's in that report. So the work item has run its custom code. There's a lot of logging present that we can inspect, see if something went wrong. And as soon as this is successfully ran, then the resulting zip file will be downloaded to Vault. So APS has finished configuring the configure products from CPQ and needs to check in the results. The intermediate stages are buffered in Vault as zip files. So the final result zip is picked up and opened in Inventor and checked into Vault. So that's opening the generated drawing and check in this document. So this is downloaded from Vault, from a bucket from APS, opened in Inventor and checked into Vault. So by opening all the drawings present in the resulting zip file. So the managed job completes its task of checking in the generated model and signals back to the main orchestration that the design automation process is complete. The quote in CPQ is put in the next state as defined in the workflow, meaning the approval state was approved and an attachment was added to the queue. So I was building the model. Now you can see that the quote I started from is now approved and has an attachment, the PDF, generated in the design automation process. And you can see in Vault, the model was checked in. So the structure is defined, is custom defined on the naming. So you got your assembly, you got your ETO part, and you got your drawing in your Vault environment. So the engineer now has the ability to review and release the model so that Vault items are created and can therefore be used to integrate with other ERPs, like other external systems like ERP. As you have noticed, there are a lot of workflows processing running side by side. Let's add another one. So the workflow inside a work item. So the work item is started in APS. The workflow executes custom code which is defined in the uploaded app bundle. APS has no knowledge of any CAD models unless it was part of the copy design. So, but when the custom code requires a component from your Vault system to be placed in your configuration, we can step out of the APS environment and call a function, a REST function from Cardiac Organized Vault REST service. And this returns a data stream which represents my, my component, and I can put it back in my APS process in my design that I'm running at the moment. So this open network from APS is nowadays standard. We used to, in the old days, we had to request it from Autodesk. This is standard functionality now. Some more info from behind the scenes. So code snippets of the several platforms that are part of the CTO automation process. Many integration platforms pretend to be low code, no code, but at a certain point of time, functions need to be coded via traditional languages. This additional programming can be made easier by providing some kind of frameworks, so it resembles more like scripting. So in this example, you got some in CPU some snap code. For the work item, you code in C#. Connect script uses TypeScript, and the connector is actually a wrapper class in APS API. Here you see a sample of a customer of us, Van Wijnen, a construction company in the Netherlands. About 5 years ago, they started with their CTO journey. At this moment, they produce houses and even blocks of houses fully automated from sales to factory. The facade configurator is giving creativity to architects to set specific characteristics of the outside walls of each house. Within the CPQ system, the price is calculated. The quote is generated, permit application documents are created. And it even results in a CAM file, handed over by the integration platform to the bricklaying robot that constructs the facade. Another customer, HTC Parking and Security, builds speed gates for securing and parking garages, hospitals, commercial areas, and also military terrains. They started their CTO transition 3 years ago. Already 2 platforms are produced, fully automated by CPQ to production. In this example, you see within design automation, how a receipt from CPQ is used to automatically create all the models, production documents, and bonds. So in this specific case, the quote consists out of 3 elements. So there was a door, there was a fence, and there was the speed gate. So you got 3 process jobs. Each process job does its own thing, creates its component, and afterwards all these 3 components are being assembled into one project assembly. The drawings are being generated for production purposes. Still processing. So there are a lot of drawings automatically being generated and bill of materials updated. Finally, the assembled job. So you see the 3 parts are being assembled. And then as last is the manage job, which picks up that assembly and starts checking in all the drawings and CAD models used for this project. And as soon as those parts are being placed into Vault, you can release them. Items are being created and used to be integrated into, let's say, an ERP system. So I think this rounds up the explanation I want to do to fully cover the entire process from start to finish, starting a CPQ to finish the Vault of an automated design automation process. We thank you for your interest and hope you learned something about how to implement such process.